Okay, in this unit we're going to talk about rational functions. And so the first lesson is on the reciprocal of a linear function. Before we talk about the reciprocal of a linear function, let's look at the definition of a rational function. So rational functions have the form f of x equals p of x over q of x, where p of x and q of x are both polynomial functions, and q of x cannot equal 0. So basically for a rational function, you have to have a polynomial in the numerator and a polynomial in the denominator. And any value of x that can make the denominator equal to 0 creates a restriction on the function. Okay, just like we saw last year. So we'll look at some examples and non-examples. So an example of a rational function is the one that we have here. So we have x squared plus 1 in the numerator and 3x plus 5 in the denominator. Since both the numerator and denominator are polynomial functions, then the entire fraction represents a rational function. Okay, and as you can see on the side here, there is a restriction on the value of x, since x equal to negative 5 over 3 would make the denominator 0, so it creates a restriction. A non-example is g of x, where the numerator is 1 plus x, and the denominator is the square root of 2 minus x. So because the denominator part is not a polynomial, it's actually a root function, then it's not a rational function. Okay, so the top and bottom both have to be polynomials in order for you to have a rational function. And again, there's a restriction there. It doesn't matter whether or not it is a rational function. Any value of x that makes the denominator equal to 0 creates restrictions on the function. Okay? Okay, so since division by 0 is undefined, rational functions have restrictions on the value of the variable in the denominator. So there's a restriction on the value of x that you can have. So one example here we have is 3x plus 5, and we know that any value of x that'll make this equal to 0 will become a restriction, and so that value of x would be negative 5 over 3. Okay, you might also have an example where you have a quadratic function in the denominator. Again, that's a polynomial, so that's okay. And so you might possibly have more than one restriction in the denominator. And in this case, we actually have 2 restrictions. If you try to solve x squared minus 9 equal to 0, you get x plus 3 and x minus 3. And so that tells you that x cannot equal positive and negative 3. So that's the restriction that we have there. Okay. So specifically, we're going to look at the reciprocal of a linear function in this lesson. And so the reciprocal of a linear function has the form f of x equals 1 over kx minus c. Now, it doesn't necessarily always have to be 1, as long as it's a constant value in the numerator, like 5, negative 3, whatever. As long as it's a constant, you could still look at it as a reciprocal of a linear function. So really, a reciprocal of a linear function means that you have a linear function in the denominator of the rational function. So as a result, there are some restrictions, and the restrictions are any value of x that makes the denominator equal to 0. And so in this case, it would be c over k. And so graphically, what that restriction looks like is a vertical asymptote. So you would have a vertical asymptote at c over k. And then finally, because you have a rational function, certain values of x will sort of make the graph approach a certain horizontal line, but it'll never touch it. And so what that creates in the graph is a horizontal asymptote. And typically the horizontal asymptote is at y equals 0. But if the graph has been shifted up or down, so if I add a number at the end here, and if I shift the graph up or down, then the horizontal asymptote could potentially change. Okay, but the horizontal asymptote is at y equals 0. Since as you plug in larger and larger values of x, you'll get a very, very, very small value for y as a result, but it'll never equal 0. And so you have a horizontal asymptote at y equal to 0. Okay, so horizontal asymptotes indicate the general behavior of rational functions as x approaches positive or negative infinity. So we're looking at the ends of the graph. Okay, so we're trying to see as the graph approaches positive infinity towards the right or negative infinity towards the left, what the behavior of the function is like. And typically the horizontal asymptote tells you that behavior. So the function approaches a horizontal asymptote either from above or from below it. Okay, so here's our horizontal asymptote here at y equal to 0. And so in this example that I'm looking at, all I've drawn is a horizontal asymptote and a vertical asymptote. What I'm trying to see is whether the function would be approaching the horizontal asymptote from above it, which would mean the function is slightly higher than the horizontal asymptote, or whether it'll approach the horizontal asymptote from below it, which means that the function would be slightly less than the value of the horizontal asymptote. For example, if you're comparing the end behaviors here to see whether it's above the horizontal asymptote or below the horizontal asymptote, really what you're checking to see is for a really large or for a really large value of x, whether the function is positive, which would mean it's above the horizontal asymptote, or whether it's negative, which would mean it's below the horizontal asymptote. Okay, so to determine the behavior of the function near the horizontal asymptote, you would want to evaluate the function for a very large and a very small value. Okay, so typically values of x equal to 1,000 and x equal to -1 are pretty good at helping us interpret whether the function is, the horizontal asymptote is being result to interpret whether the function is approaching the asymptote from above it or from below it. Okay, so the next thing we're going to be looking at is graphing reciprocal functions. So to graph the reciprocal of a linear function, we want to consider the following. We want to know where the vertical asymptote is and where the horizontal asymptote is. These two sort of create a barrier for your function, and so it's important to know where those two are initially. And then x and y intercepts sort of help us plot a point in the graph or points in the graph. And then the behavior of the function near the vertical asymptote and the end behaviors of the function. What these two help us figure out is when you are looking at a vertical asymptote, what you're trying to figure out is whether the function is getting higher, or so whether it's increasing towards positive infinity or whether it's decreasing towards negative infinity. So for example, if I'm trying to see the behavior to the left of the vertical asymptote, I want to know if it's hitting positive infinity or if it's going to start approaching negative infinity. That's what I'm trying to figure out. In the same sense, if I look at the function on the right-hand side of the vertical asymptote, same idea, I want to know if it's approaching positive infinity or if it's approaching negative infinity. And in this case, certain behaviors than others. Okay, so those are the kinds of things you want to think about. So that's the list of things that we're going to be thinking about when we graph the example shortly. For example 1, we're going to complete the table to describe the behavior of the function as x approaches each key value. So if you look at the function that's given, f of x equals 1 over x plus 7, you'll notice that there's a couple of things that I've already drawn here. First of all, I know the vertical asymptote is at x equal to -7, and the horizontal asymptote is at y equal to 0. So if I just sketch that really quickly, there's my vertical asymptote at x equal to -7, and the horizontal asymptote at y equal to 0. Okay, what we're going to be checking to see is what the behavior of the function is going to be like to the left of the vertical asymptote, to the right of the vertical asymptote, and then as the function approaches positive and negative infinity. Okay, so you'll notice that the key values in the table here are -7 with a little plus sign on the side, and we'll talk about what that means, and the -7 with a little minus sign at the top, and we'll talk about what that means as well. Positive infinity and negative infinity. Okay, so the first part of this chart, looking at -7, looks at approaching the vertical asymptote at x equal to -7 from the right hand side, and then approaching the vertical asymptote at x equal to -7 on the left hand side. So basically what you want to think about is if I choose a number that's really close to the vertical asymptote but slightly to the right of it, I want to be able to figure out whether the function is approaching positive infinity or if it's approaching negative infinity. And so I'll choose a number slightly to the right of the vertical asymptote, like -6.99. And if I take this value and I plug it into the function, so if I look at f of -6.99, so I'm trying to evaluate 1 over -6.99 plus 7, and that gives me a value of about 100. Okay, so because it tells me that the value is about 100, that tells me that I probably have a point all the way up here, and so the function is probably approaching positive infinity, okay, since it's increasing. In the same way, I'm going to choose a value of x that's slightly to the left of the vertical asymptote to get an idea of what's happening to the function slightly to the left of the vertical asymptote. So if I choose a value that's a little bit to the left of it, like -7.01, okay, so it's very close to it, and I substitute that into the function. So if I look for f of -7.01, what I end up getting is an answer of -100. Okay, and so that tells me I probably have a point all the way down here somewhere, and so most likely the function is approaching negative infinity since it's decreasing and it's going downwards. Okay, so that tells me that the function is probably doing something like this. Okay, so far that makes sense because one part of my graph is on the upper right, and the other part of the graph will be on the lower left. Okay. Then what I'm going to check is to see what the behavior of the function is around positive infinity and around negative infinity. Okay, so I just need to choose a really large value for x. So a large value for x like 1,000. And if I solve for f of 1,000, I get an answer of about 0.00099, and then it continues. And so what that tells me is, if I look at a point all the way on the right-hand side here, it's slightly higher than 0. So it sort of gives me an idea that the asymptote is probably being approached from above it. And I know the asymptote is at 0, and so it's getting closer and closer to 0, but it's approaching it from above. Okay? So what that tells me is, as x approaches positive infinity, f of x is approaching 0 from above. And then we'll do the same thing to figure out what's happening to the function as I approach negative infinity. So I'll plug in a very small value for x, like negative 1,000. And if I evaluate f of negative 1,000, what I end up getting is negative 0.00100, and it continues. And so what that tells me is, I have a very, very small value for the function again. So it's very, very close to 0. And most likely in this case, it's approaching 0 from below, because now I have a negative number. So probably a point somewhere along here. And so it's sort of doing something like this. Okay. And so this tells me that the function would be approaching 0 from below. So here it is approaching the horizontal asymptote from below. And if I sort of connect the behaviors close to the asymptotes together, I sort of get an idea of what the function would look like. Okay, so those are some key values of x that we're looking at. So approaching the vertical asymptote from both sides, and then approaching the ends of the graph, positive infinity and negative infinity. Okay, so that's why this example was important. We'll apply something similar to it in the next example.